Swayam Prabha. Digital India. Educated India.
Good morning. Welcome you all to this lecture in this series on analytical, spectral and microscopy applications of inorganic compounds and nanomaterials, which we have been going through. I made into first two parts. The first part we have looked at analytical applications, wherein we have looked at the atomic absorption spectroscopy. We also looked at the thermal methods, a huge number of thermal methods we have looked at. Then later to that we looked at the electrochemical methods, and later to that we also looked at the magnetic methods. So we have done quite a few of these analytical ones. Now we are well geared to get into the spectroscopy kind of an applications in that. So we will look at the spectroscopy applications quite wide in range. So for example, we will have why the spectroscopy applications are required, because if you wanted to characterize the compounds, if you want to follow some reactions that are happening, if you want to understand the catalysis of a process, so in all these things, either you will have to characterize a product or an intermediate or any kind of a transient, all those kinds of things. So therefore, for all of them, the basic thing is the establishing, characterizing, sometimes quantifying. So this spectroscopy will help both in the qualitative manner and as well as quantitative manner. And so therefore we will, because certain areas, the peaks, intensities will tell you quantitation, the positions, etc. will tell you the quality or the specifics of that. So therefore we can use a host of spectroscopy methods in order to explore the characterization of not only the products, even when the reaction is going on, when there are some intermediates are there, so that you can establish the whole reaction sequence. So I just focus your attention to this particular slide. Some of the techniques that I am going to cover in this particular course, maybe in the next let's say 10, 12, 14 lectures or so, or maybe 16 to 18 lectures or so. One is electronic absorption spectroscopy. Of course, we will come into details. This itself tells you it is an electronic transition and there is an energy is being absorbed, and that is what you study. And this will help you in understanding the material, molecule, compound, intermediate, any of those. A second technique is that, so you in the previous one you looked at the electron getting excited. In the second case, you look at the emission. The excited electronic state does not stay permanently in that. So therefore, the excited electronic state returns back to the ground state by giving certain light, and that is what you will study in the emission spectroscopy. So each one of these is one different technique, and we are going to spend 2, 3, 4 hours on each of these technique, 2, 3, 4 classes on each of these one. Then we will look at the mass spectrometry, which gives you the mass of a fragment or a molecule or a species, any of those things. So based on that, you can establish various aspects of it, even including the structural aspects, by integrating them. Then in many cases, we have already we know that in the transition metal complexes, the transition metal ions have got different electronic configurations. Some of them could be unpaired electron situations, which would result in the electron paramagnetic resonance. So this electronic paramagnetic resonance, electron spin resonance, you can study for organic radicals, you can study for almost all inorganic complexes, transition metal complexes, all of those where we have. The Mossmeyer spectroscopy is a slightly different one. This is a nuclear transition, wherein the nucleons transiting from one nuclear state to another nuclear state, wherein it uses a very high energy like the gamma radiation, and therefore you study the corresponding spectroscopy. But this is very limited because of the availability of the source for the Moss-Boyer, and then we will be restricting in our course only to the iron based ones, though there are a few more nuclear most commonly studied. Then we will also look at another spectroscopy, photoelectron spectroscopy. So therefore we look at the photoionization processes. So that leads to the X-ray photoelectron spectroscopy, the electron spectroscopy for chemical analysis, everything again for the quantification of this, detection of this, identification of that. Then we will also look at on the extended X-ray absorption fine structure, which is a very specialized technique which will talk about the immediate surrounding of a metal nucleus, that is the primary ligation. And this is very important in biological samples, particularly where you have the metalloproteins, metalloenzymes. So we will look at some examples, particularly of the molybdenum based ones, etc. Then we will also look at vibrational spectroscopy, wherein we use the infrared spectroscopy as well as a Raman of these things. Then we will also look at some NMR spectroscopy. We may not look at so much of a routine NMR spectroscopy in the inorganic system, but we may look at slightly different one where the paramagnetic based, and how such a paramagnetic based ones, which is completely avoided in organic NMR spectroscopy, but completely taken in by inorganic spectroscopists, and to explain certain aspects of it, including the structural distance, many kind of things. So these are some of the different spectroscopy techniques that we are going to look at as we move across. So in all these, what do you have? You have your molecule, you call it as a matter, and then you have a radiation, which you call it as electromagnetic radiation, or a light, or any kind of a light with a particular wavelength, etc. Now what you are studying in this spectroscopy, spectroscope, that's where the thing is that. So you look at the interaction of such a radiation with the matter. So therefore it does depend upon the chemical nature, physical nature of that, arrangement of this. All of these are important when the electromagnetic radiation interacts with the matter. So an electromagnetic radiation, so it itself tells you electric component or electro component, magneto component of that. So you can see here on the slide, have a look at this slide. There are two kinds of running waves shown, one with the vertical, one with the horizontal. Vertical here refer to the electric field, horizontal refer to the magnetic field. So it has an electrical component, it also has a magnetic component. Okay, so that is why it is called the electromagnet. Now when such a light or electromagnetic radiation is incidented at a compound or passing through a compound, then many things will happen, because your molecule also has got atom, molecule, your compound also has got molecules, atoms, electrons, then electric fields, not only electrons, electric fields formed by them, because it is not one atom you are looking at, you are looking at an ensemble. So therefore your electromagnetic radiation fields would in fact interact with yours. That is how you study the spectroscopy of this. So you look at this particular picture here, so you can look at the wavelength component and then the amplitude components, etc., which we will not go into details because it is not a course of the physics, but just bring it to your notice, make yourself familiar. Now when we say electromagnetic spectrum, it goes from very low energy on this right side. Please look at the slide. So here this is a frequency. So this number of times that it changes its phase, that is what the cycle, and as the number increases, the frequency increases, the h nu, therefore the energy is increases. So energy is increasing from right to left, the frequency is increasing from right to left. Now if you look at the lambda, which is a wavelength parameter, which you have seen here, wavelength parameter will be the different reverse. The higher the energy, lower the wavelength, the lower the energy, higher the wavelength in that. Now if you look at gross classification, this You have components of the low frequency, little bit higher frequency, intermediate frequency, very high frequency. So there is very low energy, somewhat little higher energy, little greater energy, somewhat more as the energy increases, very high energy components. So components going from, if you go from the high energy to low energy, then you have a gamma radiation which is very high energy. So that is where you use, if you want to break some chemical compounds, if you want to bring a fission kind of things onto the compound aspects of it, not real nuclear fission, it's a molecular kind of a fission or breaking. Then X radiation again, and then UV. Then you have UV is ultraviolet, and then you have a visible range. Then you have an infrared, which is somewhat lower energy than the visible. Then you have a microwave, and then you have the other kinds of radio waves, and then you have the very long range video waves. So you have a very long range of the wavelengths. So going from a very small, tiny wavelength to a large wavelength, very low energy to a high energy as you go from right to the left. Within the visible, if you look at, you have a spread over between the lambda 350 to around lambda 750, roughly about 400 nanometers, roughly about that. So you have that, the violet, blue, green, yellow, orange, red kind of a things that you can see, which is visible. Okay, so visible, so therefore you can see the colors can come into these ones. That's where you are able to look at these. Okay, so now just want to tell a few more aspects about this. So you have a radiation which is a very highly impactful matrix or molecules, and they can ionize, they can break the bonds, etc. And you go to this side, they are not so much of an ionizing kind of thing. So therefore these are used for non-invasion. It does not affect your biological tissue, etc., whereas these kind of things can affect the biological tissue. Both of these have got their own applications in different contexts. I'll be explaining on the next slide these application aspects of it. So both of them have got, in certain cases you need to penetrate, you need to break, etc. In certain cases you should not disturb, you should still probe. Both of these things are there. So let us look at the next slide. As I have already mentioned to you, from the if you go from here left to right, frequency is increasing, energy is increasing, the wave number is increasing, then the wavelength is decreasing. Okay, so E is equal to h nu, and that hc by lambda, hc nu bar. So the nu bar and the lambda are inversely related, and they are the one and the same but used in different kinds of units. Now you can look at in a little different perspective. Have a look at this particular slide, please. These I have already brought to your notice. See the applications of the lower energy kind of things with a higher frequency, radio and television. Then you go to the microwave. Microwave brings a lot of heating because of this vibrations of those dipoles there. That will bring the heating part of it, and the heating used in the cooking, the radar, telephone, Wi-Fi, all kinds of things. Then you have infrared, again a certain level of heating, IR lamps, IR cameras, which I'm sure you must have heard. These cameras have been used even in space applications to capture the things on the Earth's surface from the height. So you are aware of that. The visible for the colors, photosynthesis is by that, and you know the visible lights, etc. Ultraviolet, slightly higher in energy, therefore they can be used for killing the probes, sterilizing, and even for certain kind of a synthesis. Then X radiation. X radiation is used a lot nowadays in the health sector and security diagnosis. X-ray scans, it's a very common routine thing that you understand today. And then is the gamma radiation. The gamma radiation is used only to very highly sterilize, when you wanted certain kinds of foodstuffs, etc., to completely remove certain unwanted things, not to infect those, So you can do that kind of things. Then radiotherapy, chemotherapy, all kinds of things will come into this. So you have seen the frequency range, energy range, application ranges, and the difference between the, it is the same feature, both the lambda and the nu bar, but different units of that. So I think now you should be very bit conversant with moving between the centimeter inverse, nanometer, centimeter, which is a normal distance, the frequency, wavelength, so all of these, and the ranges of this. I will also show you in a while in the spectroscopy, what kind of a spectroscopy requires what region of this. I will come back in a while. So before that, let us look at the nature of some of these electromagnetic waves. So electromagnetic wave in the physics you might have already studied. We are not going to go into the details of this. You can see wave 1, wave 2, obviously this is wavelength is 1 by nu 1, 1 by nu 2 kind of things. They are different. Now if they overlap or superpose in them, you can get this kind of a structure, which is the kind of a beat pattern. You can see when you combine this, you can subtract this, you can add this. Not only 1 and 1, you can add more than 2, more than 3, any number of things you can add, subtract, etc., because the light wave is reflected from each center in the matter. At the end, what you are seeing is a combination of all of these. So that is why this. So the physics, I am not going into the details of this. So here one of the, you also have seen the refraction. You try to dip let's say your pen or pencil into a glass of water and see that your pen or pencil portion which is inside the water looks as if it is bent. There is not bent there, we know very well. That means it is the light which is bent. So that light bend property is a refraction. So it depends upon the refractive index of the medium. So that is where, and that again you study in the physics, you must have already studied. So that is because the light velocity changes from one medium to another medium. So based on that, you can also have the light coming from different sources or centers, etc. This, if it is a matter, you can talk to atom centers, to molecular centers, to electron centers, or otherwise here in the optics you look at as the two orifices wherein the light waves are propagating, and you can see the overlap of all this. The overlap of all this is nothing but the diffraction, and that is what is equivalent to. So instead of this, you have your crystal, and the crystal has got different lattice sites. These lattice sites will act as if they are like the B and C and O kind of things. So you can get a diffraction pattern. So diffraction pattern will have a relative intensity and the distance parameters. And you can also have the angular parameter, and which is explained over here. And this is what they use in the diffraction, which most popularly known as N lambda is to the sine theta kind of thing in the diffraction. So this I will go later stage when I come to the microscopy level. I will explain those things in that. So that the sine theta part will be there for diffraction aspects of it. Okay, as I mentioned a while ago that which portion of this electromagnetic radiation is useful for what kind of a spectroscopy. At the end, that is what we are interested in this particular course, not with the physics part of it. Now look at this particular slide. So we have on one end we have the gamma ray, which is very high energy, and it has a wavelength range of 0.005 to about 1 angstrom or so, very, very tiny kind of a wavelength, so very high energy. This can be used for the nuclear transitions, and in fact, as I mentioned to you, we'll use in one of the spectroscopy. In our case, it is called the Moss-Bayer spectroscopy. Then X-ray. So X-rays are somewhere around 0.1 to about a few angstroms kind of thing. And this can be used for the electrons which are a little bit deeply buried. So for example, for an atom, the 1s, 2s core levels. For a molecule, the bonded levels which are core. These kind of levels, so you refer to inner electron. So such kind of electrons you can ionize or dislodge So therefore you can study those kinds of things. So we will be looking at, for example, photoelectron spectroscopy we will be using, though it is not written here, but we have that topic in this particular course. And then we can have the vacuum ultraviolet, slightly higher energy than the ultraviolet, which is below 200 nanometers, and this can be used for the little bit of core electrons but mostly bonding electrons. Then ultraviolet, so this ultraviolet can also be used even in the this photoelectron spectroscopy. So ultraviolet visible absorption, emission and fluorescence can come from the 200 to 800 you have seen. Partly there is ultraviolet and remaining is the visible. So the ultraviolet would try to bring more of a high energy gap electron transitions, like to sigma star, that kind of things, whereas to pi star, etc. can be brought visible kind of radiation. So with this, what kind of a spectroscopy can be studied? UV visible absorption spectroscopy. The actual title is electronic absorption, and then fluorescence emission or electronic emission. So the excited state bring. So both those methods we are going to study, both those two techniques we will be studying using this kind of a radiation. Then infrared absorption and Raman scattering, as I mentioned to you, we are going to study this in the vibrational spectroscopy. So we will be looking at this vibration. Microwave is used for the rotation of the molecules, but we will not be studying in this particular course. So electron spin resonance can be studied by using this radiation, which is the microwave, another slightly level of that, which is having 0.3 centimeter inverse of the wave number kind of thing. So this we will be looking at the electron spin resonance, going from one electron spin state to another electron spin state. So then comes is the nuclear magnetic resonance. We will be looking at all this. So almost all of these regions, as I talked to you earlier here, so we will be using for some kind of a spectroscopy or the other. So we are using this for the Mars Bayer, we are using for this the X-ray photoelectron spectroscopy. Later on we will be using for the X-ray diffraction. We can use for the electronic transitions as well as the photoelectron, both UV, and then visible can be used both for the electronic absorption, electronic emission. IR can be used for the vibrational spectroscopy, and the microwave can be used for rotational, but we will not be studying. But we can use the microwave also for the electron spin resonance kind of things, etc. So all of these we will be studying in various ways, and those which in the range of megahertz range can be used for NMR. This particular frequency, the 10 power 8, 10 power 9 can be used for the electron spin resonancy, and 10 power 6 will be used for the nuclear magnetic resonance, etc. So up to this we will be using. We will not use this. These are used into the electronic applications and your other transmissions and those kind of things. So here we are looking at the interaction, the different types of different wavelengths, different energies of the electromagnetic radiation with matter. That's what we are. So I think that is what roughly the background that we need to build in, and I think now we can move smoothly into the first topic on this spectroscopy. This is electronic absorption spectroscopy. It's also referred in common as UV visible spectroscopy. Most often people will forget the visible and they'll say UV, but UV is only, in the regular UV is only somewhere around 190 to 350, 370 kind of a nanometer. This is the regular UV, and below that is called the ultra vacuum ultraviolet spectroscopy region, that is something like 20, 30 to about 180, 200 kind of thing. So most often the color, other things. Why this commonly known? Because most of the organic compounds will give in the ultraviolet region. That's why people have started using this term of UV. But most of the inorganic ones, they use both UV as well as the visible. So therefore, please try to utilize UV visible. Otherwise, you can use the term electronic absorption spectroscopy in a better sense in that. Okay, let's look at absorption, electronic absorption spectroscopy. That's what you are talking about. So electronic absorption, as I have already mentioned earlier, spectra. So therefore, it is the absorption of light leading to the electron transition from a ground to an excited state. So what do you measure? So you measure the how much, what type of light, what region of the light is being absorbed by the matter, how much is absorbed by the matter, and how does that differs from one molecule to a different molecule to a different, that means one compound to the different compound to the other. That means it depends on the nature of the compound, and it also depends upon what kind of a chromophores you refer it as. Those which are absorbing are referred as a chromophores. So therefore, different chromophores absorb in different regions. So therefore, that is the chromophores, they absorb different regions of the energy, different extents of energy, of the light intensity. So different extents of light absorbance. So you're basically looking at you irradiate with the electromagnetic radiation and start measuring how much is absorbed basically, and that what is dependent on the your compound nature, the chemical nature, at times even the physical structure, arrangement. Many of these things do matter in that. So just see in a simplistic way, how do we look at that? You have a light source giving your light, and of course you have to focus, and then you have a monochromator is the one which because this light has got a variety of wavelengths. So these variety of wavelengths are fanned out. So they are fanned out like this, the red, the orange, the yellow, etc. you can see, and you can permit one of those by using certain kind of a slits, etc. not a problem. Many things are known very well, and then you focus this light to make, and this is your cuvette, means a sample compartment, and then the light is being absorbed, and whatever is coming out you measure. It's called the detector. Whatever you measure, you can call also photo cell, etc. So this is the simplistic way of looking at. Now you convert into a numerical value, and this can happen at every wavelength. Whatever the wavelength you can resolve, that is the resolution. So if I can have 280 at one value, 281 another value, 282 another value, so I can get it every 1 nanometer. If it can be a 0.1 nanometer, I can get it 0.1 nanometer. So all these data will be collected at different wavelengths and then connected together to form a spectrum. So I will show you the spectrum in a while as we keep moving across. So I hope that is. Now there it was shown a very primitive kind of an instrument, but most often you take your compound in a solution. Sometimes you take a compounds of mixture, even in the solid state, etc. So therefore you need to subtract the background of it or the solvent of it. So therefore you require not one beam, you require the 2 beams of that. So let us take this as your a lamp. This tungsten lamp will give you in the visible range, and the deuterium lamp will give you in the UV range. You can switch over the lamp whatever you want, and this lamp light can be focused, and this will grating. Earlier I showed you a prism. The grating, the purpose is the similar, but the principle is different. Purpose is similar, principle is different. Now you make the break into the light beams, and then take it into one range into sample and another by the reference. Then you can subtract these two, and then you can go for the detector. Now you have seen from a single beam in the previous slide to a double beam in this one. The same thing from another source I have put, but there is nothing different. So you have your the light source, the diffraction, and then you allow one particular wavelength, and then you allow to go to this side and this side. So you have a sample, you have a reference, and then you can make, and then you collect it at every fraction of the wavelength or a wavelength numbers, wavelength values, and then you can form a kind of a structure that. So that is what is called the spectrum. So the spectrum will have, one is the x-axis, other is the y-axis. The x-axis is you're changing the wavelength, so there is lambda versus the absorbance. So I will explain that a little bit more when I start in the next class on this. So we'll look at the characteristics of this such a spectrum, and that is what main concern of this particular topic on the absorption spectroscopy, any spectroscopy. Finally, a chemist will not have much interest in this instrumentation, etc. But though I have given you a little bit of idea as to how things are going on, but what chemist is more worried about is how to interpret this particular thing, a spectrum, how to derive the parameters, how to derive quantification, how to derive pKa, how to derive stability constants, how to derive protonations, deprotonations, very many kind of reactions, how to establish the structure of the compound. So all of these can be obtained from this particular spectrum. So we will look at those details as we keep moving across this particular course, and so I will stop at this stage for this topic, but we will be continuing in the next couple of hours looking at characteristics of this particular absorption band. Also we will go to further in interpreting this, how you can apply a lot of applications as well. Thank you very much.